Good day to you from Chem Help ASAP. Just like one can model enzyme activity mathematically, we can do the same with receptor activity. On the screen is the equilibrium of a ligand and a receptor to form a ligand-receptor complex. An idea arose that the complex is what actually causes the response. The receptor doesn't cause the response. It's the bound receptor that causes the response, the complex. Therefore, the way to get maximal response is to get maximal complex formation. This became known as Clark's occupancy theory. Percent complex formation equals percent response. When all the receptors are bound, then the response will hit 100%. That's interesting. How does percent complex formation change with ligand concentration? Ligand concentration of a full agonist. Here you go. Look at the top curve. The y-axis can be percent complex formation or percent maximal response. Well, this looks a whole lot like what we saw with enzymes. This looks like a saturation curve of an enzyme. It's the same curve. As it turns out, the math is the same too. We're more accustomed to looking at response curves with a logarithmic axis. See below. But the curve on top is equally valid. Now let's look at the math. On the top left is the Michaelis-Menten equation. On the bottom left is Clark's equation. They are the same, except we switch Kd in place of Km and Emax in place of Vmax. Notice that Clark's equation is set up to accommodate the different agonists. A full agonist would have an Emax of 1. A partial would have some number less than 1. And a superagonist would have an Emax greater than 1. There have been extensions to Clark's equation. Here is one. This adaptation includes an extra term, E0, which can be included if a receptor shows constitutive activity. Other tweaks are possible. While Clark's theory does not model the behavior of all receptors, Clark's theory is the most commonly encountered ligand-response model. I hope you found this video helpful. Please subscribe, like, or leave a comment. Take care.